Okay, so for this definition, we want to construct the 6 trig functions. And it's worth mentioning that if you have studied the 6 trig functions before in the terms of the phrase SOHCAHTOA, that is not what this video will be talking about. We're going to talk about how to construct the 6 trig functions using x, y, and r, which are values commonly associated with the Pythagorean theorem, or sometimes referred to as a, b, and c. So, if we look at this right triangle that shares a point with this circle, we know that a circle can be constructed with some radius and then a rotation of 360 degrees given a bunch of different angles, theta. And if we take this triangle to have a hypotenuse or terminal side that is intersecting with the circle at this point here, and it forms a right angle when we bring down this side y to meet the x-axis, then we now have a way to relate r, theta, and x and y. We can do that with these 6 trig functions because these 6 trig functions represent ratios of x, y, and r with our angle theta. Sine of theta, this is written sine, but this is pronounced sine but written sin theta. So it's not sin theta if you've ever heard it pronounced that way. Just like this is not cos theta but cosine theta. This is not tan theta but tangent of theta. And likewise, these are cosecant, secant, and cotangent. We'll discuss those in a moment though. Sine of theta is just like the square root function or a logarithmic function or an exponential function. You are plugging this angle into the sine function just like you would plug 4 into a square root to get 2. It's worth noting this because a very common misconception is that you are multiplying sine to some angle theta. That doesn't happen any more than you would multiply a square root to 4. That doesn't make sense, just like multiplying sine to theta doesn't make sense. So, we are saying with these 6 trig functions, if you plug theta into each of them, you will get a certain ratio of the sides of this right triangle. Sine represents the first ratio, which is the y value divided by the r value, y over r. Cosine represents the ratio of the x value divided by the r value. And tangent represents the ratio of the y value divided by the x value. Once we know these 3, we immediately know the other 3. I've lined them up like this for a reason. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent, meaning just flip the fraction over and you have the other value. So cosecant of theta gives you r over y. When you plug theta into the cosecant function, you get the ratio r divided by y. Secant is the reciprocal of cosine, which will be r over x. And cotangent is the reciprocal of tangent, which will be x over y. These are the ratios of the right triangle that help us compare theta to our x and y values and our r value, which represents the terminal side, hypotenuse, so on, or radius of this circle. So with all of this, let's see if we can't find the 6 trig function values of some angle theta given the point on the terminal line of theta, 3, -4. Meaning if we were to graph the point 3, -4, we would have a point roughly here. And if that point is on the terminal line, then to construct a triangle based on this terminal side, remember the angle measurement always starts from the positive x-axis if you're not given the initial side, but we don't need the exact original angle. We need a reference angle to quickly find the 6 trig function values. And the reference angle is always found by taking your terminal side and connecting it to the closest part of the x-axis, which means we take this terminal side that we just constructed and connect it to the closest part of the x-axis, which is right here, to create a right triangle. This will give us a reference angle to theta, which is all we need. We know 2 of the sides of this triangle because we know it goes down 4, which is negative 4, and it goes to the right 3, which is positive 3. You might be wondering, how can we have a negative side of a triangle if you've studied geometry in the past and they told you you cannot have that? And they're right. You cannot have a negative side of a triangle unless that triangle is placed on the origin and lined up exactly with the x-axis and y-axis. Suddenly, these represent distances based on the axes, so you can measure them in terms of positives and negatives. Keep that in mind. If this triangle were just off in space, then we would just put 3 and 4, not negative 4. So from here, we now need to find this hypotenuse. To find that hypotenuse, we can go back to the Pythagorean theorem because this is a right triangle. This value r, when you square it, will equal this value 3 squared plus this value negative 4 squared, which gives us r squared equals 9 plus 16. So we get r squared equals 25. If we take the square root of each side of the equation, we get r equals plus or minus 5. And it's important to note, this side of the triangle is not referencing the x-axis or the y-axis, which means it can't be based in a measurement from vertical or horizontal perspective, so it will always be positive. So it's just the positive 5 value here. Now, if we were solving for the x value or the y value, they can be referenced off the x and y axes. Those answers could be negative. The hypotenuse never will be. So, now that we have all 3 sides of the triangle, we can use our formulas. We have sine of theta, cosine theta, tangent theta, and cosecant theta, secant theta, and cotangent theta. Sine of theta is equal to the y over r. So that is negative 4 over 5. Cosine of theta is x over r, which is 3 over 5. And tangent of theta is equal to the y over the x, which gives us negative 4 over 3. Remember to find cosecant, secant, and cotangent. Just keep them lined up so that you just find the reciprocals. Cosecant is the reciprocal of sine. You would get negative 5 over 4, since we don't leave negatives in the denominator. For secant, you would get 5 over 3. And for cotangent, you would get negative 3 over 4. And this is our list of values that tell us the 6 trig function values of our angle theta.